The title of my talk is Synchronization Problems in Computer Vision. And my talk is based on the following paper, co-authored by Andrea Fusiello, that is a survey of many methods from many authors with a unifying view under this general framework of synchronization. My talk will follow this outline. I will give an introduction to synchronization and then focus on a specific solution, which is the spectral solution. Then I will show how this method can be used to solve many problems in computer vision, like structure from motion, registration, and many others. And finally, I will give some concluding remarks. So I will start with an introduction to the problem. And in particular, as already mentioned, the main motivation for studying this general framework is that it can be used to solve many problems in computer vision. And here you can see many examples that I will review during this talk, like structure from motion, registration, matching, mosaicing, and even motion segmentation. These problems may look a bit different at first sight, but they have many things in common. First of all these problems can be represented as a graph. Of course, depending on the problem, the nodes will represent different things like images, point clouds, and so on. But in all these problems, the key thing is that these nodes are in relation, and these will be represented by some transformations that are in particular elements of a group. In particular, we will see rotations, permutations, and other groups that can represent many problems in computer vision. Before moving to the general definition of synchronization, I will start with a simple example that also explains the origin of the term synchronization. Here we have a network of nodes where each node is characterized by an unknown state, and pairs of nodes can measure the difference between their states. And here the goal is to infer these unknown states from the pairwise measures, as shown in the figure. And this is the scenario that gives the name to synchronization, since it refers to clock synchronization, where the task is to synchronize clocks in a network starting from pairwise offsets. Starting from this example, we can generalize this problem, and instead of real number, we can consider a group that has an operation. And hence we have the general definition of synchronization, where the task is to recover these elements of a group starting from their differences or ratios, depending on how we call the operation. We can represent this problem as a graph where edges correspond to the unknowns, edges correspond to the observations, and nodes correspond to the unknowns. And we always assume a connected graph. The link between unknowns and the measures is also called the consistency constraint, and basically it is the same as the definition of synchronization. Hence, we have that each measure defined on an edge is the ratio between the corresponding elements defined on the nodes. The solution to this problem is not unique because it's defined up to a global group element. And this can be easily seen from the fact that we can multiply all the elements by the same quantity, and this quantity simplifying the product. And hence, starting from a solution, we can get many other solutions. However, this is not a problem in general, since we can easily fix this ambiguity, for example, by fixing the value of one node and setting it to the identity. The simplest way to find a solution to this problem is using a tree of our graph. And more precisely, we can fix this global ambiguity by setting the root of this tree to the identity, and then we can find a solution for the remaining nodes by propagating the consistency relation along the tree. And hence we will use both our measures and values on the nodes already computed to find values for the new nodes. However, this solution is subject to error accumulation since we propagate errors along the tree, and this is why we need a better solution in practice. In other terms, we need to achieve error compensation, and this can be done by exploiting redundancy in the measures in our graph, and hence consider all the graph and not only the tree. Now we will see an example of a solution that achieves this task, which is the spectral solution. For explaining this solution, I will focus in particular on matrix groups, hence groups that have a matrix representation, since they are very common in computer vision. And in particular, we will start with the case of the general linear group, which is the set of invertible matrices of a given dimension that we call D. As before, we have our graph representation where nodes are the unknowns, edges are our observations, and these are related by the consistency constraint, where here we have the product of a matrix and the inverse of the others. The key idea for solving this problem with the spectral solution is to conveniently group all the variables and all the measures in some block matrices. And in particular, we can collect all the measures in a block matrix Z, where each measure is placed in the right block depending on our graph. In a similar way, we can collect all our unknowns in this block matrix X, where we put the values on the node one under the other. And thanks to this matrix representation, we can prove the following result, which gives a relation between Z and X. And specifically, this says that the columns of X are the eigenvectors of Z with eigenvalue n, where n is the number of nodes in our graph. In other terms, the product between Z and X is a multiple of X. And this is an important result since it gives a practical way to find X and hence to find a solution from the eigenvectors of Z. Before reviewing this solution, we will move to the case of missing data, whereas in the previous slide, we considered the simplified case of a complete graph. If we have missing edges, then these are represented as some zero blocks in our big measurement matrix. However, we can still derive a spectral solution by slightly modifying our measurement matrix. And in particular, we can consider this new matrix W, which is derived from Z by scaling it in a proper way. And the scaling matrix is derived from the Kronecker product between the identity and the degree matrix of our graph. Then it can be proved that the columns of X are the eigenvectors of this new matrix W with eigenvalue 1, which is the largest eigenvalue. And in formula, this means that the product between W and X is equal to X. Hence, also in this way, we can derive a solution from the eigenvectors. In other terms, starting from our measurement matrix Z, we can compute W just by properly scaling this matrix using the degree matrix of our graph. Then we compute the eigenvectors of this matrix, which are properly collected in a new matrix U, which can also be viewed as a block matrix where each block corresponds to a node in our graph. Then we can multiply by the inverse of the first blocks, all our blocks, in order to have the identity in the first place. And this will fix the group ambiguity. In this procedure, it is important to observe that we don't need to compute a full eigenvalue decomposition, but thanks to the previous results, we only need the deal leading eigenvectors, where this is the size of the matrix, of each matrix. Hence, for example, if we are working with 3 times 3 rotations, we only need 3 eigenvectors and not all of them. In addition, if we have a sparse graph with a few edges, then we can even exploit sparse eigensolver to further improve efficiency. This solution has been explained working with general matrices that are invertible, but it can be easily extended to any subgroup of invertible matrices. And here you can find many examples. For example, it can be used for rotations, it can be used for rigid transformations, permutations, and many other examples. And what are the differences between these subgroups? The method is the same, there is only one step that is different. Specifically, following the general solution for synchronization, we start with a graph that has these observations on the edges. We first compute the eigenvectors of this matrix, and then we multiply by the inverse of the first block in order to fix the ambiguity. Then we need to add an additional step compared to the previous solution, which is a final projection that depends on the group. And this is required since the spectral method works with the linear algebra only, and it does not enforce specific constraints of the group elements. For example, if we are working with rotation, it does not enforce the property that rotations have a unit determinant and are orthogonal. And hence we require to enforce these constraints at the end in order to produce a valid solution that represents the required values on the nodes. And this final projection is basically what changes between each group and each application, in addition to how we construct our input graph. And now I will detail what happens in all these groups shown in the previous slide with reference to specific applications in computer vision. And specifically, I will start with the structure from motion. Structure from motion is the formal name for 3D reconstruction from images. And the task is to recover 2 things. One is camera motion and the other is the scene structure, where the former refers to camera rotation and position, whereas the latter refers to the 3D coordinates of the points, where the input are many images of a static scene captured by multiple cameras. There are many different approaches for structure from motion. Here we focus on a specific class of methods, which is called global structure from motion, which separates solving for camera motion and solving for scene structure. And in particular, we focus on camera motion only here, and more specifically, we will consider only the rotation components of the cameras. And the reason for this is the fact that recovering camera positions cannot be viewed as a synchronization problem since we have a scale ambiguity. In this specific problem, we can view camera rotations as elements of the special orthogonal group, which is the set of 3 times 3 matrices, such that they are orthogonal, hence the inverse is equal to matrix transposition, and they also have unit determinant. We can recover camera rotations in 2 steps. In the first step, we can easily recover the rotation between each pair of cameras in isolation. And this will produce the measures in our graph that are associated to edges, where each camera is associated to a node. In the second step, then, we can recover the global rotations associated to each node starting from pairwise ones. Specifically, The first step is something that is extremely standard in computer vision. For example, we can recover the relative rotation of a camera from the so-called essential matrix, and which can then be factorized into rotation and translation using singular value decomposition. Then, after this has been done, we can go to step 2, which is exactly a synchronization problem. In particular, this is a rotation synchronization, since we are dealing with rotations, where the consistency constraint has the matrix transposition in place of the inverse due to the structure of rotations. And hence we can follow the general pipeline of the spectral solution, where we start with our graph with observations on the edges that are relative rotations now. We compute the eigenvectors, we fix the ambiguity, and then for the final projection, we have to solve the problem of computing the nearest rotation to a given matrix. And this is a known problem that can be solved using singular value decomposition. And this will produce our absolute rotations defined on the node that solve for camera rotations in structure from motion. Another relevant problem where we can use this spectral solution is 3D registration. In this problem, we have many point clouds that are recovered independently, and we want to bring these point clouds into alignment in order to recover the object. Here we have a similar problem as before, and in particular, we are working with the special Euclidean group that is the set of 4 times 4 matrices that represents these rigid transformations. In particular, these matrices have a rotation block, a translation block, and the 4th row is made of 0s and 1. As before, we can frame this problem as a 2-step approach, where first we solve our problem for pairs of views in isolation. And this produces the measures on the edges of our graph. Then we compute the global transformation starting from pairwise ones. As before, the first problem is something that is standard in the literature. There are many solvers, such as the well-known iterative closest point algorithm and even more recent methods. The second step instead is exactly a synchronization problem. And in particular, this is called motion synchronization, and it is formulated in the special Euclidean group. Hence, also in this case, we can solve 3D registration using the spectral method. And hence, we first solve many independent registration problems between 2 views in order to produce our input graph with these relative transformations on the edges. And then in order to recover the absolute transformations, we proceed as before, computing eigenvector, fixing the ambiguity, and then to the final projection. That in this case is done similarly to rotations using singular value decomposition. Another relevant problem where we can use this framework is image mosaicing. As shown in the figure, the task of image mosaicing is to align multiple images into a mosaic. Here we can represent the problem using homographies, which are 3 times 3 matrices defined up to scale. And in particular, since there is this scale ambiguity, a convenient way is to represent them as matrices with unit determinant. And this is done by scaling these matrices to unit determinant. And this permits to avoid the scale problem and at the same time working on a group, which is the special linear group. As before, the problem is solved in 2 steps. First, we align pair of images in isolation, and then we refine this pairwise alignment in order to get a global alignment. Also in this case, the first step can be solved using standard techniques from multiple view geometry based on computing homographies. And then these homographies are scaled to unit determinant. Our focus here is the second step, since it is a synchronization problem. In particular, is a synchronization problem defined in this special linear group. And hence, also in this case, we can solve the problem using the spectral solution that has the same structure as before. Concerning the final projection, that is the step that differentiates between all these problems, here is extremely simple, since we can we only need to scale matrices in order to get unit determinant, and this is done by dividing each matrix by the third root of its determinant. Then we now see another application, which is image matching. In this case, the task is to find matches or correspondences between multiple key points that are present either in images or in 3D point clouds. In this case, we can conveniently represent matches as permutation matrices that are binary matrices with zeros and ones, such that columns sum to 1 and rows sum to 1. And also this form a group, which is called the symmetric group. And in particular, the size is given by the number of key points that are present in each image. And as shown in the figure, given some matches between two images, we can conveniently represent them as a permutation matrix. Given this representation, we can solve as before the problem in two steps. We first compute matches between pairs of images in isolation, and then join these pairwise correspondences in order to get multi-view matches. The first step is quite standard. There are many techniques, from handcrafted methods to deep features, whereas the second step is a synchronization problem called permutation synchronization. And here, similarly to rotation, the inverse is given by matrix transposition. We can apply also in this case the spectral method, where the final projection coincides with the problem of finding the closest permutation to a given matrix, which is a linear assignment problem. Now we will move to our last application of synchronization, which is motion segmentation, where the task is to cluster key points in multiple images based on moving objects. Hence, in this case, we have a dynamic scene. We can first solve this problem on pairs of images in isolation, and then combine these partial results to get a multi-frame segmentation. And in particular, the first step is once again something standard. It is an example of multi-model fitting, where we are required to fit many fundamental matrices to correspondences in order to cluster points into images. And then in order to combine these partial results, we can solve a synchronization of binary matrices. In particular, as shown in these figures, we can conveniently represent clusters as binary matrices, where ones corresponds to points in the same cluster. And we have the same consistency constraint as the case of permutations. Here, the math is quite different than before, because in this case, we don't have a group, in contrast to the other applications, but using similar reasoning, we can still derive a solution based on the eigenvectors. In particular, we can set these block matrices as before, and it can be proved that the columns of X are eigenvectors of Z, where the eigenvalues are distinct in the case where each motion contains a different number of points, and the number of eigenvectors is equal to the number of motions. In this case, the final projection can be done just by rounding the solution to binary entries, and this can be done by looking at maximum values over rows of the matrix that contains our eigenvectors. Now I will move to some concluding remarks. In this talk, I focus on the spectral solution, which is an approximate solution. As mentioned, it does not enforce geometric constraints, but it needs a final projection. However, it has many advantages. On one side, it involves a very simple implementation, just a spectral decomposition and a final projection. In addition, it is a very general solution, and this is the main power of this framework, because the same math can be applied to many groups and many different problems. It's important to mention that this is not the only available solution for synchronization. There exist also other solutions that exploit other tools, but these solutions are specific for the chosen problem. For example, they can be valid only for rotations and not for the other tasks. Concerning more in general synchronization, we have seen that this is a two-step framework, and this permits to exploit two-view tools. And hence the problem is split into sub-problems that involve two images, 2-point clouds, and so on only. And these sub-problems are easier to solve, and sometimes we even have closed-form solutions. In addition, this permits to exploit a more compact representation of the problem, since it is solved in the space of transformations without using explicitly points after computing the pairwise measures. However, we can have suboptimal results since we are not considering all the information, but we get a global solution that promotes error compensation. And most of all, it involves many different problems in computer vision, such as the ones that we have seen here. This concludes my talk. Thanks for your attention.
Okay, sorry, let me try that again. Thanks for the very nice talk, Federica. Any questions from the audience for Federica?
Hi, Federica. Thanks for the great talk. This is Kasra. So my question is about, you actually talked about it in your conclusion remarks. So as you mentioned, so these spectral solutions are extremely elegant. They can be applied to any of those problems that you mentioned. But then, as you mentioned, there are these alternatives like local optimization, or lifting the problem to a larger space and then convexifying it and then projecting that to a feasible solution. I was wondering, in what situations you think I should use spectral relaxations and spectral solutions that you describe to these types of synchronization problems?
Actually, this solution can also be viewed as some sort of initial guess that is used to start other methods, even more sophisticated, that employ some nonlinear optimization.
I see. So we can always use them as to initialize these other optimizations.
Yes. Yes, in the case where the solution is not satisfactory, it is always useful to have something good to start with.
I see. Thank you. There's another question.
Thank you very much for your great talk. When I listened to your talk, the kind of like immediate problem I was thinking of was multiple robot case where you can only measure the relative distance among the maybe robots, and therefore maybe you can measure the relative distance among the nodes where you have the kind of like a graph edges and so on. The problem is, as you just mentioned, the solution is not unique in this case. So you have like some issue. That's the first problem. Second, you have also some measurement observation noises where you can't really measure the distance properly among the nodes. Do you have some, maybe this is a big question. Do you have some idea how you can remove, in this case, the ambiguity about the solution uniqueness? And second, if you have the measurements noises, in this case, do you have any specific kind of recommendations how to take this problem forward for this kind of problem?
Okay, I will start with the last question. I mean, due to time constraint, I did not speak about all the details, but this method can also be extended to some sort of weighted case where we can put a weight inside each measure that represents how reliable a measure is. And these weights can also be updated during the process. Hence, instead of having a one-step approach where we compute eigenvectors one, we repeat the procedure, we update weights, and this is similar to iterative reweighted least squares, where weights are useful to reduce the impact of noise or even outliers. Concerning the similarity with the distance-based localization, actually the problem is similar, since also there we have a graph, we have measures, but due to the definition of synchronization, we need a relation of this form. For example, the difference between values, the ratio. In the case of distances, we have a more complex function defined on the edges, but we can, I think, reason in the same way for the ambiguity and, for example, fix the location of one node in some way.
Great, thank you.
All right, actually, I have one more question for you, as long as I have you here. So I was very interested to see that you were able to extend the synchronization approach to handle problems where the elements of estimation were not necessarily elements of a group. So for example, the case that you mentioned involving binary matrices. I was very curious, have you looked at applying a similar technique like that to partial permutation synchronization? Because oftentimes, you know, if we want to do point matching, we don't necessarily have exact correspondences for all the points in all the frames in question.
Yes, I mean, I did not mention here because there was no time, but yes, it is possible to extend to partial permutations as well. The problem is a bit more complicated because in that case, we don't know the number of eigenvectors, since it corresponds to the ideal number of trajectories in our images, and we don't know in advance, but it can in some sense overestimated. Yes, in this paper, for example, we work with partial permutations, and even other authors have worked on this.
Okay, awesome. I will definitely be checking that out then. Thank you. Any other final questions for Federica? Okay, great. Well, let's thank both of our speakers again. Yeah, thanks especially to both of our authors for agreeing to speak remotely at what I'm sure is a very unpleasant hour. So,
thanks for inviting.
Okay, great. So I guess maybe let's take a quick 15-minute break, and then we'll reconvene at 3:45.